All right, so this week we learned about flavors, energy, and we came up with 4 important flavors of energy. We came up with the energy of motion, of movement, which we're going to say EM. Came up with the energy of stored gravitational, which we said was EG. We came up with elastic energy, which is EE, and we came up with thermal energy, E thermal. And so in this video, we're going to quickly go over some of the factors that affect these types of energies, and we're going to create equations for solving quantified values for these energies. So we'll first start with the energy of movement. So EM. EM is going to depend on 2 things. Energy of movement first depends on mass. If you have something traveling with a small mass going this way, and you have something traveling with a large mass, let's just say they're traveling the same speed, we can say that this car has a greater amount of energy due to the amount of mass that it carries. It has the ability to produce more change. One way that we could figure out how that is possible is if we created, let's say, stacks of cardboard boxes over here. This is an example I used in class. If we made a wall of cardboard boxes and we drove this car into it, and this car into it, we would see a lot more change of those cardboard boxes with this large mass because it contains a lot more energy stored in its movement. So, first thing it depends on is its mass. The second thing it also depends on is velocity. If we had another car that was the same size as our first car, let's say this one is the same size as this one, but it was moving extremely fast at a huge velocity, it would be carrying a lot more energy than that first car. So the equation that results for energy of movement is equal to 1/2 the mass times the velocity squared. So there's our equation for the energy of movement. All right, let's take a look at gravitational energy. So E G, stored gravitational energy depends on, well, it depends on, the first and easiest one is, of course, gravity. And the question is, how much gravity? And if we're on the surface of the Earth, which a majority of our problems are going to be, that gravity, the acceleration due to gravity, equals 10 meters per second squared. So it always depends on that 10 meters per second squared because gravity The gravity field near the surface of the Earth is 10 meters per second squared. What else does it depend on? Well, we saw in a couple examples in class that we know that there's a presence of gravitational energy when something has a height associated with it. It has the ability to fall. Some might say the potential, which is one way we can talk about this, the potential to fall. So it also depends on height. If we increase the height of something, let's say that there's another ball up here. If we increase the height, let's say this is that height, then it would gain more gravitational potential energy. So it depends on how high something is off of the ground. Now, we talked about this in class on Friday, that we need to then, if we're going to say it depends on how high it is off the ground, well, the ground is kind of arbitrary. We need to call this is the point where the gravitational energy equals 0. So this is the lowest point on our example. Now there might be, let's say there's a downstairs to this house that we're looking at, and there's a basement where there's a new level. Well, this basement is not really important. Yes, potentially the balls could fall further, but we want to just cut it off, and we're going to say we're looking only at this as our example. So we're going to call this R, call this the reference level. Reference level is where EG is equal to 0. And you choose it. You choose. You can choose where it's going to be equal to 0, which makes the most sense. All right, so we got gravity, we got height. The other one, for those of you that were in class, we saw when we drop, let's say this is a, let's put two balls at this height, so that they're the same height. And let's say that this is a bowling ball, and let's say this is a basketball. Now, we know that the bowling ball has quite a bit more mass than the basketball. If both of these fell from that height, and let's say that they fell onto some cardboard boxes or maybe a piece of wood, or someone is trying to catch them or something, the bowling ball would do a lot more damage to these boxes than the basketball. This has the ability to produce more change when it falls the same height as a basketball. So the last thing that this depends on is the mass of the object. So our equation for gravitational stored energy is equal to the mass times the acceleration due to gravity, which on the surface of the Earth is always going to be 10 meters per second squared, times the height. And this height is from the reference level. All right, so that takes care of our gravitational energy. Let's finally look at stored elastic energy. Elastic energy. So if we've got a rubber band that sits like this, we know that we could stretch that rubber band to something like this. We could stretch it out, maybe using our fingers. When we look at how much energy is stored in this rubber band once it's been stretched, one really important thing is the distance that you stretch it from the equilibrium. We could probably all agree that if I stretched it this far, it might be getting pretty close to snapping, but it might definitely is going to travel a little further if you stretch it further, or you can almost feel the amount of energy that's being stored in this demonstration more than in this. So this is one stretch, and here's another stretch. Elastic depends on how far object, because it doesn't always have to be a rubber band, changes its shape. Now notice that I said changes its shape. So we measure from the equilibrium where it's not stretched. It's not the total distance from here to here. It's just the distance from where it started to where it got stretched. So it depends on how far the object changes its shape. And the second thing that elastic energy depends on is the type of object and how elastic the object is. If we had a rubber band, let's say we have another rubber band, we're going to stretch it the same distance than this, but let's say it's a really thick rubber band here. Well, that thickness of the rubber band actually allows more energy to be held inside of that rubber band. And the thickness of the rubber band and the elasticity of the rubber band and the elasticity of any object affects how much elastic energy can be stored. So another thing that it depends on is the quality of elasticity. Quality of elasticity, that's a funky kind of long way of saying that. Basically, every single object that can be stretched or compressed has a constant value associated with it that we call the spring constant. And this basically tells us how much energy can it store per some length it's stretched or compressed. So elastic has an equation that involves how far something changes its shape and the quality of elasticity, which we're going to call the spring constant. It's similar to the movement. It's 1/2 times the spring constant times how far shape is changed. How far shape is changed. And that value is squared. So let's get that on here. That is the equation for the elastic energy that can be stored in something that's compressed, stretched, or its shape has changed. Okay, and finally we want to talk about the unit of energy. What is the unit of energy? In class, we did a little derivation. We said we know that the gravitational energy equals, I'm going to abbreviate, the mass times the acceleration due to gravity times the height, mg times h. We also know that the energy of movement equals 1/2 the mass times the velocity squared. So what I asked some students to do was some unit analysis, meaning we know what mass, acceleration, and height all would be measured in. We know what mass and velocity would be measured in. If we take out the units of those values and put it in, we might be able to find out what the unit of that EG might be. So let me give you an example. We know that the unit for mass, we measure mass in kilograms. I'm going to put it in a little bracket here. We measure the acceleration due to gravity, it's an acceleration, in meters per second squared. We measure height or any length or any distance in meters. All right, so there are 3 units. Now, they're all multiplied together, so we can simplify these into one kind of big fraction. Kilograms, meters, and meters will all be on the top. So it's kilograms times a meter, and the only thing that'll be on the bottom is seconds squared. All right, let's take a look over at this one. The 1/2 is really not important. It's just a number. It doesn't have a unit to it. So we're just going to focus on the units. Mass, again, measured in kilograms. Velocity, measured in meters per second. But notice that value is squared. So we're going to square our units. Notice I squared both. It is not meters per second squared. It's meters squared over seconds squared. If we neaten this one up, it's going to be kilograms times meters squared over seconds squared. And if you look at these two, we notice with a little bit of simplification here, these two meters, yes, come together to make a meter squared over seconds squared. And we see that we get the same unit on both sides here. And that's because stored gravitational energy and the movement energy are both energies. That's all they are. It's energy. They should be measured in the exact same unit. Even though they're stored in a different flavor, like gravitational energy or movement energy, they both have the same unit, kilograms times meters squared over seconds squared. Now, there's a long way of writing the units every single time. So what's been done is a kilogram times a meter squared over a second squared is proportional to a fancy word called a joule. And we're going to write a joule as a capital J. So energy is measured in joules.